To remind you, in the previous videos, we had shown that a wave does not have a specific point in space. Therefore, the idea of a vector pointing to its specific location has no meaning. The wave is spread out throughout space, possibly miles, maybe forever, and it has no specific one location. So we're going to have to come up with something different to define its location. Likewise, we can't take the derivative or the change in a position vector, its displacement, divided by a change in time to find a velocity. We're going to instead have to come up with some new idea for doing how to measure the propagation of this disturbance. So let's show you the video again to show you that although the oscillators move individually up and down, the propagation moves horizontally and the wave is spread out through space, so you can't say exactly where the wave is. So how are we going to describe the wave? Well, we've been doing it for a long time, probably without you even knowing it. For instance, we talked earlier that when you dropped a pebble into a pond, you see ripples, and you watch those ripples move through, and you talk the ripples as the wave. Now what the ripples really are is the point for the peak. That is, if it was a sine or cosine, you'd be saying, for instance, if it was a sine, that's where it's a maximum. That's where the angle was 90 degrees. And you watched how that place of 90 degrees moved through space over time. This idea is what is called a phase front, as in the phase angle of 90 degrees. It is a geometrical surface of constant phase. It could be the peak. That's usually what our eyes pick up, but it doesn't have to be. And what we're going to do is watch the shape of that phase front, whether it's circular, flat, spherical, whatever, and watch how it moves through space over an amount of time, just like you did as a kid watching pebbles drop into a pond. We're also going to find another new quantity, a ray. This is an arrow perpendicular to the phase front and pointing in the direction of the propagation of the wave. In other words, it points in the direction that the disturbance is propagating, not the direction that the oscillators are propagating. So in our video that we just watched, it would have been pointing horizontally in the direction that the wave moved. Now let's go and look at this with the pebble problem. So we take our pebble and we drop it into the lake here, and what we see is a set of ripples that are formed over time. And if I'd done a bit better, I would have drawn nice circles. These ripples, in fact, the disturbance is everywhere. The ripples represent the peaks, and those peaks represent the phase fronts. The rays are perpendicular to the phase front, like this, and show that the phase front is moving out in all directions. So this here, that's a phase front, and this there is a ray, and the rays are perpendicular to the phase front. So it says that if you were here, then that part of the wave, if you were like a surfer on a surfboard, would be going in that direction. If you were over here on it, the wave would be taking you in this direction. If you were down here, it would be taking you down. And these would represent the high point on the wave where you'd want your surfboard. Now, you can choose any point. It doesn't have to be the peak, but the peak is easiest for us eyes. So in this case, what we're looking at is what we would call circular waves. And they're circular waves because phase fronts are circular. If you were to do this in 3-dimension, you would get spherical waves, which is usually what happens when something oscillates. Now later on in the next semester, we'll oscillate charges, and these ripples that we see will be electromagnetic waves that can be radio or television or even light. As another example of that that's pretty useful is an example where we have something called a plane wave, and it can be described by the following formula. It looks an awful lot like our oscillator, but now we have two things in here, not just one, inside of this angle. One of them has space, kx, and the other one has omega t like we had before, which represents time. And if we tried to plot the shape of this, let's say where this is x, y, and z, we would find that if you vary y or z, nothing happens because y and z are not in the formula. So let's say that the cosine here was of 0 degrees, and so this formula was a. This formula would be a no matter what value of y or z you put in. So all along this surface, this plane, for a given value of x, in this case x equals 0, the value of this function is the same. Likewise, you could give a different value of x, and you would have a new plane, which would all have the same value. Also, because I've done a little bit of studying, I know that if I was to change time, then in order for this thing, for instance, to keep an angle of 0, if I increase t, this would make this a negative number. To keep the whole thing 0, x would have to become positive. That means this plane would in fact move to the right in this direction, the positive x direction, over time. Those are the rays. This turns out to be an extremely useful example of a wave because it helps us to derive formulas and do other things, and also it's not as complicated with having a curved shape. Now, what's useful about this wave, among other things, is that even if you have something that creates circular or spherical waves, like this, if you get very far out and you have an antenna or whatever that's not too big, then you only see maybe this much of the wave. And if for all intents and purposes, after this wave gets very far out, that wave almost looks flat. And so we can use the simpler math of the plane wave when dealing with more complicated problems involving spherical or cylindrical waves. This is known as a far field approximation in engineering and science, and it turns out to be quite useful. If you're very close where you can't ignore this curvature, they call this the near field, and that means you're near your source, like your antenna or television station. We will not be doing any more of that sort of stuff in this course. That would be something you would have to do if you wanted by becoming an engineer or science major in college. Now, let's look at how we can use this plane wave to help us find out some stuff. We have this formula, and I'm going to choose a particular angle. Now, I can choose this angle for anything I want, but I'm going to choose it such that at t equals 0, x equals 0, and delta equals 0. So initially at t equals 0, at the origin, everything in this was 0, and this function had a peak. In other words, although I didn't draw it, right here you were on the peak, and there was a peak that went out this way. There's a plane all the way along that origin. And I want to see what happens to that peak over time. Well, kx minus omega t is equal to 0. So at t equals 0, x is 0 in order to make that equation true. That's where the peak is. Now I want to wait a time t. This is the time for the oscillator or the wave to go up and down. and I want to find out where that peak is. Now, at one period later, the formula would be kx minus omega period t, and it would be 0. But we know some things. Omega t is equal to 2 pi. This is from oscillators. So we have kx minus 2 pi is 0. Well, we can use that. That says that kx is 2 pi. But k lambda is 2 pi from our definition of the wave number. So when we put that in, we have kx is equal to k lambda. So therefore, the new position is lambda. What does this mean? What this tells us is the following. This peak has moved over a distance lambda in a time that it took this guy to go up and down, t. Now, we can use this to find the speed of a wave. We have that v is delta x over delta t. But that's just going to be equal to lambda over t. So that's the speed of the wave. But that's the same thing as saying that it's lambda f, because f is 1 over t. And you can prove that that's the same thing as saying that it's omega over k. So if you know the wavelength and period, you know the speed of the wave. If you know the wavelength of the frequency, you know the speed of the wave. And if you know the angular frequency and the wave number, you know the speed of the wave. All right, that finishes this video.